right. Good morning, everyone. My name is Tanya Bloch. As Robert said, I am from Israel, from the Faculty of Civil and Environmental Engineering at the Technion. And yes, this is kind of different, so there are no LLMs here. The topic of this is exploring the applicability of computer vision models for automated compliance checking. So very briefly about the background, since all of you already know this, currently compliance checking is performed mostly manually by experienced architects and engineers who review design documents, usually in 2D drawings, right? They produce reports of issues, communicated back to the designers for corrections, and that process repeats until no more issues are found. So obviously this is a very time-consuming, repetitive, and labor-intensive process, and we would like to automate it as much as we can. The common practice in automating compliance checking is a rule-based system where we translate regulations into sets of logical statements, sets of rules. The design in this case is usually given as a BIM model, and that BIM model has to be processed as well to make sure that the information in that BIM enables the execution of the rules. And then we have rule execution and reports. Unfortunately, some parts of this automated compliance checking process are still mostly manual, and that is the processing of the regulations and, of course, the processing of the BIM model. And that usually either falls on designers that have to follow long lists of information requirements during the design itself, or on the checkers that have to make sure that the information in the BIM matches the expectations of the checking engine. We have seen over the years quite a lot of efforts in this domain and quite a lot of technologies being explored in this domain, including AI and machine learning technologies. The one subfield of machine learning that unfortunately we have not yet seen explored in the domain is computer vision. So computer vision is a branch of machine learning that involves training algorithms to interpret and classify visual data, and that is usually done with convolutional neural networks. And we truly have amazing abilities in computer vision today. We can see on the slide only part of the possible applications. There are many, many more. And still, unfortunately, the potential of using this technology to support ACC has not really been explored. And so this is exactly the aim of this work, to evaluate if information extracted from simple 2D floor plans using computer vision techniques can support regulatory compliance checking. So to do this, we focused on a small set of regulations from the sanitary installations code. So mostly these are requirements about the minimal dimensions of individual elements, but also usage areas around plumbing fixtures. So this free space that you're supposed to have around plumbing fixtures. So there are also some relational aspects involved in these checks. And our starting point, as I said, was a very simple image of a 2D floor plan. And the idea was to extract all the needed information from that 2D floor plan using object detection models. In this case, YOLO 11 was chosen to support downstream compliance checking. So this is the proposed pipeline. We start with data collection and data processing because these models need to be trained. In this case, we trained two object detection models. One was responsible for identifying and isolating bathrooms in the entire big floor plans. And then another object detection model was responsible for detecting the smaller objects within the bathrooms. That was then the input for a set of rules implemented in Python for the actual compliance. So going back to the beginning about the data set, there are existing data sets for object detection on 2D floor plans. Unfortunately, they were not designed to support compliance checking, and so some information is missing in most of them. So some of them, for example, they only have like walls and openings, and that's it. Some of them don't have reliable information about the scale of these floor plans. And this is important because we don't want to just detect and classify the objects. We also want to extract information, at least about the bounding boxes of these objects, to be used later on. So we've decided to collect our own data set, and everything that was collected was in a unified scale. So we've collected things from permitting applications available online, from industry partners, but everything was in a unified scale. It was also then continuously processed, of course, and annotated and tagged. We used the RoboFlow engine in this case, which was very convenient for the data management. All the objects were also annotated with additional attributes that reflects whether they're compliant or not compliant to the code. So we have not just data for object detection, but also the ground truth for the actual compliance check. Okay, so after quite a heavy augmentation process, we've ended up with 736 total images of floor plans that were completely annotated. Unfortunately, this is quite small still for object detection, but this is what we had. So we had to shrink down the list of requirements that we wanted to check based on the objects that we had good representation of in this data set. That's what we did. So we could see the results of the two detection models here. Model 1, as I said, responsible for identifying the bathrooms in the entire floor plans, and you can see the F1 score 0.84, which is quite encouraging considering the small data set. And then the second model, the actual object detection model, did an even better job with an F1 score of 0.9. So this was then the input for a set of rules for compliance checking, and you can see the results of the checks themselves here. You can see we got quite nice precision and recall, but it was not very unified throughout all of the checks. Most of the problems that we've had were the usage area checks, which was expected kind of because they include also considerations of not just one single element, but also its surroundings. So once you get one thing wrong, the entire check goes wrong. And this is also something that we have very clearly seen and was also expected in this case, that the errors from the object detection propagate into the compliance check. In this case, we had two object detection models, so the errors actually accumulate and propagate into compliance check. But I will say again that we were working with a limited data set, so there's quite a lot of room for improvement in this sense. In terms of conclusions, so I think, first of all, I think the results are encouraging enough to justify further investigation of this topic. Obviously, there are still lots of things that we have not handled. We've done this on a very small set of regulations, of quite simple regulations. So to really understand the capabilities of using computer vision to support ACC, a lot more investigation is still needed. What we did see quite clearly already from here is the potential that this thing has for compliance checking, and not in saying that you don't need the beam anymore. That's not what we're saying. So you still need the beam. But the thing is that there is a potential here to reduce the manual workload that goes into the beam processing. So in this case, for example, we did not care if somebody put simple 2D symbols instead of the actual plumbing fixtures. As long as the visual representation is there, this would work just the same, which means that there's an opportunity here to shorten the list of information requirements that we put on designers. Just let them design how they design, and we can fill in all the gaps and still allow automated compliance checking. Sorry. Okay. Having said that, not everything obviously can be checked, but with computer vision, right? Because things that have no visual representation, we will not be able to support using this approach. So things like fire ratings, acoustic ratings, occupancies, anything that has no visual something within that beam, we will not be able to do this way, which means that different regulations can benefit from different representations and different technologies. And so in the broader sense of a conclusion about ACC, I would say that maybe we should start thinking about hybrid approaches to compliance checking, where we leverage all these different technologies and the benefits of these different technologies into one system. And computer vision now can be another tool to add to that technologies. That's it.